morning, everyone. It gives me immense pleasure to come here again for my course, Aircraft Stability and Control. Today I am in lecture number 18, that is maneuvering point stick fixed. As you know that I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. My topic for the day is maneuvering point. Before that, we have discussed about neutral point, different types of forces acting on the aircraft. These forces are the X direction force, Y direction force is called the side force, X direction we can say the drag force and the thrust force. If you say about the vertical direction, it is lift and the weight. And for the side force, and another we have the moments. These moments we have discussed the three types of moments. First one is the pitching moment. When we talk about the pitching moment, that we can see here that if this is the aircraft is flying like this. Due to some disturbance, assume some gust came from here and nose has gone up. So this motion with respect to the lateral axis of this is from wing tip to wing tip, the axis which is passing. This is called the lateral axis, and the motion along with respect to the lateral axis, especially the pitching motion, is called the longitudinal motion. In this longitudinal motion, we have the two forces and one moment. These forces are the horizontal forces like thrust, which is in this direction, and drag is in this direction, and the lift above and weight below. So these are the two forces and one moment, and so this is called the longitudinal motion of the aircraft. This longitudinal motion of the aircraft covers the pitching, and we have discussed before different types of power control and different derivatives. We have already discussed about the contribution of the wing, contribution of the tail, contribution of the fuselage, engine contribution for static stability. We have thoroughly understood in our previous classes. Today I am going to discuss about maneuvering point, and that is in a stick fixed condition. When we talk about the stick fixed, means we are not disturbing any control surfaces. Control surfaces are fixed at a particular 0 degree of the position. In today's topic, we are going to discuss about introduction and the revision, aircraft aerodynamic centers, problems and solution on aerodynamic center, trim condition, elevator position, stability requirement, and explanation of the static stability. So in this, I am going to discuss about the neutral point and the static margin. This we have already covered in some of our previous classes. It is here somewhat we are going to discuss about the neutral point and the static margin. So what is the neutral point? For neutral static stability, Cm alpha will be equal to 0. This equates to a horizontal line on a Cm versus alpha plot. The aircraft will pitch up for any angle of attack condition, and if Cm naught plus Cm IH were set to 0 and we had Cm alpha equal to 0, then the Cm characteristics would remain 0 for any angle of attack. A horizontal line coincides with the horizontal axis. So it is very interesting here to understand that for neutral static stability, if you see here, we have this plot Cm versus alpha. In this plot, we can see that this line is horizontal and it is parallel to this alpha line. The aircraft will pitch up for any angle of attack condition. So if we make any angle of attack, let it be 1, 2, 3, 4 and so on, it is up to 12 degree. The aircraft will pitch up for any angle of attack condition if Cm naught plus Cm IH. So what is the Cm naught? Cm naught is this one. This is called Cm naught. So this is the Cm naught, where set equal to 0 and we had Cm alpha equal to 0. Then the Cm characteristics would remain 0. So if Cm is equal to 0, so it will start from here and it will go in this line only. In this line. A horizontal line coincides with the horizontal axis. Theoretically, the airplane could be trimmed at any angle of attack and would not return or diverge following a disturbance. So the neutral point, it can be trimmed at any angle of attack and will not return or diverge following a disturbance. Now, the condition for neutral static stability is important because it represents the boundary between static stability and instability. If you see the equation, Cm alpha is equal to Cl alpha x bar Cg minus x bar Ac. Here Cm alpha equal to 0 is achieved if xCg equal to xAc. Very interesting to note here that if I am drawing one diagram here for the airfoil, and it is the one is the AC and another is the CG. So if xCg, if we take from here, this is the xCg, and from here to here, this is the xAc. So if this xCg here and xAc both are equal, if xCg is equal to xAc, it means what? The both point, this is the AC and this is also CG. If both are in the same point, there will not be any pitching moment. There will not be no pitching moment will be experienced. There will not be any pitching moment and aircraft will remain in the same status as it was disturbed. So that is the importance of neutral point. So locating the center of gravity at the aerodynamic center of aircraft will result in an aircraft with neutral static stability. As a result, the aircraft AC location is also called the stick fixed neutral point. So here xAc, whenever the AC is coinciding with the center of gravity of the aircraft, that time xAc will be called as a x neutral point. So in this case, if you see here that in this diagram, So I am just drawing this diagram, and you can see that what is the, this is the one diagram, this is the another diagram. Here we have the AC and here we have the CG. Slowly, if it is shifting towards the CG, on top of this, here AC and CG will be in the one point. So this AC, whenever it is on top of the CG, this is called X and P. Okay, so this point is called the neutral point. Whenever the aerodynamic center of the aircraft is coinciding with the center of gravity of the aircraft, that point is called the neutral point, and the distance from the leading edge of the wing to the neutral point is known as the X neutral point, or the distance of the neutral point. If the CG is located aft of the neutral point, but sometimes this if CG is located aft of the neutral point, okay, just I am trying here. This is the CG and this is the NP. So if CG is located aft, so here this CG is aft of the neutral point, the aircraft will be statically unstable. So if like this, till the time CG is either ahead, here is 1, here is 2, and here is 3. So this is the CG position. If the CG is ahead of the neutral point, aircraft will be stable. And if the CG is behind the neutral point, aircraft will be unstable or unstable. So that we have to understand that the location of the center of gravity is very important, and it plays a very important role for the any state of the equilibrium, and the Cm alpha will be positive. So if center of gravity of the aircraft, just you can see here, in this aircraft, this is the leading from the nose, here is the neutral point, and here is the CG. If the CG is ahead of the neutral point, there will be a moment pitch down. In this condition, it will be pitched down. Whenever the center of gravity is reached to the aerodynamic center, aircraft will be neutral, and that point is called the neutral point. That aerodynamic center, when aerodynamic center and the center of gravity both are overlapping each other, that position is called the neutral point. In case the center of gravity is behind the neutral point, the tendency of aircraft will be pitching upward, or it is in clockwise direction. The moment is in the clockwise direction, nose will go upward, and aircraft will be in the unstable, or aircraft will be statically unstable. And in this case, Cm alpha, the Cm alpha is equal to change in coefficient of moment when angle of attacks are changed. And if it is in the positive direction, we say that aircraft is in unstable condition. So this is the focus on the neutral point. So neutral point plays a very important role to understand the aircraft stability. By this equation, we can find the aerodynamic center and also neutral point. So this we have already derived. I think you remember that in my previous classes. So XAC, this is the location of the aerodynamic center. Aerodynamic center. So if we want to find out the location of the aerodynamic center, that is x bar AC is equal to x bar AC of wing and fuselage plus coefficient of lift at angle of attack with horizontal tail divided by CL, coefficient of lift of wing and fuselage at the same angle of attack, neta h SH by S, x bar ACH, 1 minus d epsilon by d alpha divided by 1 plus CL alpha H plus CL alpha WF NH SH by S, 1 minus d epsilon by d alpha. By this we can find out the aerodynamic center of the aircraft. Now we have to see what is the static margin. Till now we have discussed about the neutral point, but now we want to further discuss about the static margin or SM. Another useful concept to longitudinal static stability is that of static margin SM of aircraft. We have done these equations before also, and it is rewritten in this slide. That is, moment with respect to the center of gravity is equal to L left, the difference between AC and the distance between aerodynamic center and the center of gravity, that is xCG minus xAC plus moment of with respect to aerodynamic center. CMCG, if we divide this by half rho v square S C bar, we will get CL x bar CG minus x bar AC plus CM AC, and CM alpha is equal to CL alpha x CG minus x bar AC. So here we can see that the static margin is the difference between the aerodynamic center and the center of gravity location. So SM, static margin SM is equal to x bar minus xCG. So we can write here minus x bar CG minus x bar AC, and so is this x bar CG minus x bar AC, so we can write it at a x bar NP minus xCG. So this is static margin is the difference between the neutral point and the center of gravity of the aircraft. So this we have to very much understand, and it is in the percentage of some location, or mostly it is percentage of chord length. So static margin is simply the distance that the CG is in front of the aircraft AC normalized or divided with respect to the mean wing chord. Because CL alpha will be positive for lift coefficient below stall, it can be seen that a positive static margin will result in a negative CM alpha. So to have the negative CM alpha, CL alpha should be positive. So if you see here like this is the CL and this is the alpha. So here this is the positive. So here CL alpha is positive. So if it is like this, then only we can get CM alpha is less than 0. So to have the longitudinal stable, we should have first thing this as a CL alpha, this CL alpha as a positive, and this CM alpha should be less than 0. So this we have to ensure, And if it is CL alpha is CL naught is greater than 0. So you will get CM naught also greater than 0. So to have the longitudinal stable, CM naught should be greater than 0 and CM alpha should be less than 0 or negative, and this should be positive. If we have like this, we can ensure that aircraft is statically stable. Now thus a positive static margin results in a positive longitudinal static stable. So if very nice results are coming, if SM is positive, then it is a positive longitudinal stability we can get. A negative static margin results in negative static stability. Okay, so if you are getting SM negative or less than 0, then it is unstable. Then aircraft is unstable. Neutral longitudinal stability is associated with a static margin equal to 0, and if you are getting SM is equal to 0, it is a neutral stable. So you can say that by finding the number of static margin, if you are getting a positive number, it is a positive stability. If you are getting the negative number, it is a negative stability. If you are getting the number 0, it is a neutral stability. So here, referring the equation, here again, this CM alpha is equal to minus CL alpha and static margin. This we have to, and here static margin is X and P minus X bar CG. It should be in percentage. Okay, because this bar indicate divided by C bar. So these things are all non-dimensional. You will not get any unit of this. So CM alpha is equal to minus CL alpha into SM, and where SM is equal to minus CM alpha by CL alpha, and this is called minus CMCL. Minus CMCL, or if you draw the plot, so you will get like this. This is the CM and this is the CL. So to have the positive static margin, it should go like this. If it is like this, the value of CM alpha by CL alpha should be negative. So this is called CMCL plot. We can draw the plot of derivative CMCL. This you can see here. The derivative CMCL, the slope of a plot of CM versus CL, which is similar to a CM versus alpha plot, is directly proportional to the static margin. So the plot of CMCL, the slope of a plot of CM versus CL, which is similar to a CM versus alpha plot, is directly proportional to the static margin. Is directly proportional to the static margin. The negative of the slope of a CM versus CL graph will be the static margin as indicated in the figure which I have shown earlier. As the center of gravity of the aircraft is moved aft towards the tail, CMCL becomes less negative and eventually equals 0 when the CG is located at the neutral point. Thus, the neutral point is achieved when the change in delta E with respect to CL is equal to 0. So here this you can see that if we plot a CL versus delta E trim starting from here, if the CG is forward, Just you can see here, I am drawing here. This is the CG, again CG, and this is the 1, 2. And here is your, so AC or neutral point. So how much forward? If it is forward here like this, you will get more slope. As in this case, here of CG between forward CG and the neutral point, somewhere here in this plot, here somewhere. And if this CG has reached here in this neutral point here, then you will get a straight line, and this shows that CG is at the NP. And if it is started upward, means it is now positive. The plot is positive and it is unstable because now CG is behind here. CG. If CG is behind, the plot will go upward. So by drawing this plot, we can find out the requirement of delta E, and we can also find out that aircraft is statically stable or not stable. This type of parameters are very much essential for designing of any of the aircraft. Now, how to determine the neutral point? It is very important to find out that where is the location of the neutral point. To determine the neutral point location, in flight test, a series of trim points are flown with several different CG locations. This you can see here. This is the plot. So first case is the forward CG, second case is the mid CG and the aft CG, and we are finding out the delta E by delta CL and with X CG location. So if you see here, this is the forward location, this is the mid location, and this is the CG and in the same position, and here is aft location. So we have to fly the aircraft, and for particular delta elevator deflection, what is the CL, and if we draw with respect to the center of gravity, we will get 3 points. And if you join this and extend here, and wherever it is cutting this XCG line, this point is called the neutral point. So by this way, we can find out that where is the location of the neutral point. And why we required to find out? Because this will give the status of the stability of aircraft. At no case the CG location should go behind the neutral point. Otherwise, aircraft will be unstable, and not only statically, if the aircraft is statically unstable, it will be always dynamically unstable. So we have to ensure that aircraft should be normally statically stable in all type of situation. Here we have one small numerical. So I will go for the maneuvering flight and the maneuvering point. Longitudinal maneuvering flight includes maneuvers where the load factor is not equal to 1. So load factor is the ratio between the lift and the weight. So L by W is called the load factor, and we say that aircraft is maneuvering when lift and weight are not equal. That time we say aircraft is in maneuvering, and the aircraft has the pitch rate. So that time pitch rate will come into play. Typical maneuvering flight involves load factors above 1 where the aircraft is pulling G. So if aircraft is going upward, the pulling force is more than G, and it will be called that aircraft is maneuvering. To do the analysis of maneuvering, one additional term called the pitch damping derivative, that is called CMQ. This one new term is involved in this equation. So previously we have seen that Cm is equal to Cm naught plus Cm alpha into alpha plus Cm delta E into delta E. CMIH into IH up to here. But this new term CMQ we have added here. So for the trim condition, total coefficient of movement should be 0. This should be Cm naught plus Cm alpha into alpha plus Cm delta E into delta E plus Cm IH into IH plus Cm Q and Q, where Q is a pitch rate. CMQ provides a damping moment that opposes the pitch rate of the aircraft and acts like shock absorber. So this CMQ is like a dampers, like hydraulic damper, which in a vehicle we are putting so absorb the shock. See, this CMQ is inherent parameter which should try to damp the parameter. Because the aircraft has a pitch rate, it results from the incremental change in horizontal tail angle of attack because the aircraft has a pitch rate. This is explained here that how these things are happening. A positive nose up. It is shown here. If the moment is like this, it is a nose up pitch rate on the aircraft, that is called the Q1, produces a downward velocity at the horizontal tail. So if you see this horizontal tail, if this aircraft is going in this direction, tail will go in this direction. So the horizontal tail, which is Q1H, this downward velocity produces an increase in the angle of attack. So this velocity is producing a delta alpha H, and this delta alpha H is equal to Q1H by U1. This you can see here. So this much angle of attack is increased. The increased angle of attack in turns produces an increase in lift, which results a nose down more. So if here a lift will be increased more, and this will try to counter this moment. So this additional velocity due to the velocity of nose up will try to counter this motion. The increased angle of attack in turns produces an increase in lift, which results in a nose down moment, delta LXH, opposing the direction of the pitch rate Q1. This is where the pitch damping effect comes from. So this is the effect which is observed by this tail. This is trying to damp this moment. Okay, so that is the purpose of this damping, or the horizontal tail, and this damping, it CMQ acts like a damper. We have defined the angle of attack at the horizontal tail alpha H before in our previous classes. The alpha H is equal to alpha plus IH plus tau E delta E minus epsilon, where tau E is equal to dou alpha H by dou delta E. For maneuvering flight, delta alpha H must be added to the expression for alpha H, or alpha H is equal to alpha plus IH plus delta E minus epsilon plus delta alpha H. And an additional aerodynamic force must be generated on the horizontal tail in the opposite direction to the increased lift produced by delta alpha H. This offsetting force is generated with a change in elevator deflection, that is tau E delta E plus delta alpha H is equal to 0. So delta E is equal to minus delta alpha H by tau E. So delta E is equal to minus Q1XH divided by U1 tau E. So where alpha H is equal to Q1XH by U1, which we have already seen here in this. So delta H, it is given here. So from here we have taken this equation and we have put here that delta E is equal to minus Q1 delta H by U1 tau E. This equation will have a negative sign which indicates that increase trailing edge up elevator or aft stick is required to hold an aircraft in a positive nose up pitch rate maneuver. Now, the very important point is maneuvering point, which this lecture is intended. So here, this delta E by delta N is equal to minus CM CL by CM delta E, W by Q bar S minus G XH divided by U1 square tau E. Here N is a load factor, pitch rate is Q1 and this Q1 is given by G N minus 1 by U1. So here for the we can write for this thing Q1 is equal to G N minus 1 by U1 and so D delta E by delta N is equal to 0 for the maneuvering point. So for the maneuvering point this value should be equal to 0 and then if we solve this thing we will get the maneuvering point. So the maneuvering point is located aft of the neutral point. So always if you see here, this is the line, this is the CG, this is the NP and here will be maneuvering point. This is aft of neutral point. Mostly maneuvering point will be aft of the neutral point. The maneuvering point is located aft of the neutral point because the aided damping provided by CMQ provides more stability for the maneuvering flight cases. So if aircraft is maneuvering, then this maneuvering point will come into play and the stability criteria will increase. CMQ essentially makes the aircraft appears to have more negative Cm alpha. So this CMQ makes that Cm alpha is more negative. So I have taken this, my reference are first and foremost book which is I am referring is Yachout, TR et al. Introduction to Aircraft Flight Mechanics, AIAA Education Series 2003, ISBN number 1 56347-577-4. The second book which is very important, that is Nelson RC, Flight Stability and Automatic Control, second edition, Tata McGraw-Hill 2007, ISBN 0-07-066110, and the last but not the least, NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh from IIT Kanpur, and these are the Swayam portal of this Aircraft Stability and Control. It is very good. Professor has given very good lecture. Try to listen that thing. And thank you very much for joining this class. And if any questions, you are welcome to ask. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.